Hello, good afternoon. Welcome back. So let's do a brief review first. And the plan for today is to finish the rest parts of the minimal spanning tree problem. And last time we've introduced the problem, and we also provide a generic method for solving the problem. So the generic problem looks like this. It basically lays out the principle of solving the problem. We need to, so the results of solving a minimal spanning tree is to return a collection of edges or a set of edges, and that edge should that set of edges should be a tree that's that makes sure that all the vertices are covered, that covers all the vertices in the graph. So how that tree is obtained is obtained from a incremental process, and that is at the beginning the set is empty, and you basically need to grow that tree by adding edges to the empty sets incrementally. Like within each iteration of the while loop, you will need to select an edge from the remaining from the graph that is outside the current set, and that edge should satisfy some criteria so that it is safe. Okay, so after we defined the generic method, we actually introduced a bunch of terms like the cut of a graph, which splits all the vertices into two partitions, and the term for cross, right? So if an edge is the two ends of an edge exists in the resulting two partitions of a cut, then we say that edge crosses the cut. And also we say a cut can respect a set if there's no edges in the set that crosses the cut. So we use this bunch of definitions to define the light edge, which is the least weight, the edge that has the minimal weights among all the edges that cross the cut. So we say that a light edge is a safe edge. Okay, so this slide from slide 9 to slide 12, we basically lay out a very high level principle of selecting a safe edge. And based on this principle, we can have the two implementations, which is cross-goal and the Prim's. So the plan for today is that we cover the Prim's algorithm. So basically, cross-goal's algorithm and the Prim's algorithm, they use two different ways to selecting the safe edge. And let's review cross-goal a bit. So the cross-goal algorithm relies on the disjoint set. Okay, so the disjoint set supports several primitive operations, like initialize a set from a vertex, which is done by calling the make set, and also to find the sets that a vertex that belongs to by calling the procedure find set, and also union, which merges two sets. So given this disjoint set data structure, we're able to define this connected component procedure. So this procedure will help you find all the connected components within the graph. Okay, so the assumption for running for running this connected components graph, connected components algorithm procedure is that we don't assume that all the vertices are connected in a graph. So that's why we want this procedure to find all the connected components, okay? So, and we will later apply this connected component procedure to the Kraskos algorithm, but the assumption of a Kraskos algorithm is stronger because Kraskos algorithm is to solve the minimum spanning tree. And this assumption of the minimum spanning tree problem is that we are able to reach all vertices in the graph and they are all connected. Otherwise, it won't be a spanning tree, right? If there are some vertices that are not reachable from the source, then it violates our assumption at the beginning, okay? So roughly speaking, the connected component defined here is a more general method. And by running this example on the demo here, we're able to see that's how this connected components algorithm merges distinct joints together. As long as there's no edges, if there's edges that connect to vertices, then the algorithm is able to union the two vertices together. Okay. So what's different between the Kraskos algorithm and the connected components algorithm? We listed, by comparing the code, we can find a very significant difference, which lies at the line 4, right? We basically need to first sort all the edges by their weights. Yeah. So because that is determined by the nature of the problem, right? We want to select a safe edge, and according to our conclusion from the generic MST algorithm, and safe edge is a light edge, right? And what is a light edge? Light edge is among all the edges that cross the cut, it must have the minimal weight. So that's why it makes sense to first sort all the edges by their weight. So after we sort them, in the next for loop, we're able to iterate over all the edges in the desired order, right? So everything else other than the sorting part, it's basically the same thing that occurred in the connected components algorithm here. So an additional step is that we need to put the edges selected into the set A. Okay. So we can kind of conclude that the way that that the safe edge is selected in Kraskos algorithm is to look at the weight of the edge, right? And as long as that edge connects two distinct joints, and also it is currently the smallest, the minimal, the weights that has the minimal, the edge with minimal weight, then we can consider it for the safe edge. And another characteristic is that all the vertices are initialized to the sets. So we can think of that all the edges and the vertices, they form a all the edges in the selected in the set A, they form a forest, because it's not for sure that after each time we select a safe edge, it must they must form a tree. It is not the case. So for example, here after step 1, after step 2 here, after HG is selected, then the next one to be selected is IC, okay? Because it has the least weight, right? And then the next step is GF. So it's not necessarily true that what's inside A is always a tree. But rather it is a collection of trees. So it is a forest. And only after all these steps are done, we will have a complete tree. So in any intermediate steps, we can have multiple trees in the set A, okay? So this is a very salient characteristic of the Kraskos algorithm. And today we're gonna see the Prim's algorithm will be different from the Kraskos in terms of the way that the tree is constructed. So let me switch to the playing mode. Stop sharing and start play mode. Play the slides and share the screen again. Okay, so Prim's algorithm, and it's just another special case of the generic MST. Okay, we actually implement the algorithm based on the same thoughts, and the difference is that all the edges in A always form a single tree, not a forest like Kraskos algorithm does. So because it's a tree, so we need to start from an arbitrary root vertex R. A tree always grows from a root node, from a root vertex. And we will grow the tree until all the vertices are spanned, until the tree spans across all the vertices, okay? So now we'll need to use a new data structure, right? So it's different from the disjoint data sets that we used in Kraskos, and this time we'll need to use a minimal priority queue. So this is a familiar name, right? The minimal priority queue will be used to store all the vertices that are not yet in the tree, okay? So in the Huffman codes, we use minimal priority queue to store all the letters with their frequencies, right? So the minimal priority queue is a queue structure. It's a first in, first out data structure, but the priority is measured by a score, and the elements with the minimal score values, with the minimal values, will have the highest priority. That means the vertices that has the minimal score will be extracted first, will get out of the queue first. Let me open up the chat. So it's basically a queue-like structure, but with the priority scores with this specific way. So we need to use a queue. You need to use a key attributes for each element in the queue. Okay, so the element with the minimal key will have the highest priority. So this is some infrastructure we need to use. The queue and all the elements in the queue will have a key attribute, okay? And for each vertex, the key is defined by the minimal weights of any edge that connects the current vertex V to a vertex in the tree, okay? So if there is an edge that connects the current vertex V to a tree, there could be multiple edges, right, to a tree. There could be multiple edges to an outside vertex to the current tree, but we need to choose the minimum weight as the key value, right? Because remember the principle of finding the safe edge. The safe edge needs to be the light edge, and light edge is the one that has the minimal weights. Okay, so we need to use the minimal weights of the edge to define the key attributes. Okay, so what if there's no edge? What if the current tree is not connecting to that vertex? Then we'll simply give it an infinite number to indicate that, okay, this current is not connected to the tree yet, so we will not consider it in this round, right? But after a while we are growing the tree is getting larger and spanning to larger areas in the graph, then more and more vertices will be likely to be will become connected to the tree. All right, so let's look at the algorithm. Okay, so let's look at another other conditions. Other than the key attributes, we will also use the parents, the pi attributes, to remember the parents of the vertex in the tree. Because now we are growing a tree rather than using disjoint sets. So we'll need to use the parents of attributes. Okay, so although all the edges and the vertices are stored in the tree, and eventually it is the tree object that we return, but it's implicitly maintained a set. So for taking any vertex in the tree, we just use V to its parent to indicate an edge, right? That is an edge. From V to V's parent, that is an edge. And the V is from this set, and this set means that V is all the vertices. We exclude the vertex in the roots. We exclude the vertex roots, and we also exclude all the edges, all the vertices in the queue, because the queues are those not in the tree yet. So what's in the trees actually can be represented by this set. So we exclude the roots because the roots doesn't have any parent node yet. So that's just for the validity of the definition. Okay, so that's how we define the set A. So when the algorithm terminates, the queue becomes empty and the whole set of A becomes this thing. Then the only thing that's different is that there's no queue here because queue is empty. And at this step, we'll simply return the A, and this is exactly the minimal spanning tree we need. Okay, now let's look at the algorithm. All right, so this is the MST Prim's algorithm. First of all, initialization. From line 1 to line 5, we go through all the vertices in the graph, okay, except for the roots. So we will set the key to infinity and all the parent to nil, which is for none, okay? And then except for the vertex, for the root vertex, because the root needs to be included in the tree. So we will set the key to be 0, okay? And that indicates it's 0 distance away. It's 0, the distance from the roots is 0 from the tree itself. So, and then after the initialization, we will initialize the minimal priority queue by putting all the vertices into the queue first. Okay, we will insert all the vertices to the queue, including the root vertex, right? But since the root vertex has the smallest key, so it will be the first one being popped out from the queue. Okay, so that's initialization. Then in the main body, from line 6 to line 11, we can spot 2 loops, right? It's a bigger outside loop is a while loop. Okay, so it keeps the looping until the the queue is empty, right? As long as there is elements in the queue, we will continue run the code from line 7 to line 11. So in line 7, okay, so yeah, after, let's look at these two bullets again. Oops. So before the line 7, after initialization, all the vertices in the queue, if there's any vertex whose parent is not now, then its key will also be an actual number, a valid number rather than the infinity. And the key is the key attribute that we defined first. And it is actually the weight of the light edge from V to the parent of V. Okay, so let's look at line 7. So for line 7, we will extract the minimal, the elements that with the minimal priority, that with the minimal key values. Okay, so we'll call this extract minimal function on the queue. So it actually serves as a function to identify the vertex on the light edge that crosses the cuts. Okay, so the cut is defined by what's in the tree. Okay, what's in the tree and what's outside the tree. So everything outside the tree is in queue. And we will remove the U from the queue, pop it out from the minimal priority queue, and then insert it into the set. Okay, which is to add the current, insert the edge to the queue from U to U's parent. Okay, so another important step after we extract the minimal elements from the queue is line 8 to line 11, which is a for loop. And in this for loop, we actually go through all the adjacent vertices of the elements that's just popped out, which is U. After U is extracted from the queue, we will go through all of its adjacent vertices. And what we do is to first check whether the adjacent vertex is in queue. If so, we also need to check whether the weight from U to that adjacent vertex is smaller than the current key attribute of the adjacent vertex. Okay, if the weight is smaller than the key value, then we need to update the key values for V and also update the parents of the adjacent to U. Okay, so this may be not that easy to connect at this point, but we'll later see in an example that's why this is the case. Because if the weight is smaller than the current key, which means that we find a shorter path, or we find a new light edge to replace the old key values. So it updates the key and the pi attributes for every vertex that is adjacent. Okay, but V is not in the tree yet. Okay, it must be in the queue. If it's not in the queue, which means it's already in the tree, then we don't need to check. We don't need to update it, right? Because it's already in our minimum spanning tree. We only update those adjacent vertices that are outside the tree, that are in the minimum priority queue. Okay, so let's use an example to see how this works. I think this is the same example, and we'll run the MST Prim's algorithm on it, and we assume that we start from the vertex A. Okay, so A will be the root vertex in the tree, so it's highlighted with bold here. So its key value is initialized to 0, and Meanwhile, for all the other vertices, they are initialized to infinity. So we'll use a queue. We'll use a table to represent the minimum priority queue. So initially, all the elements are in the queue, right? From A to I, and we also include the second row. The first row is so this row is the key values. Okay, we listed all the key values here. So other than the A, all the other elements than A have the infinity as the key values. So let's go through the while loop. And apparently the vertex A will be the first one being popped out because it's the root node, right? It's popped out, and we need to, by the code, right? We need to examine, the code says whenever a node is extracted, we need to go through all of its adjacent vertices, right? What we have is B and H, right? B and H are A's adjacent vertices. And they are indeed in the queue because they are all not in the tree yet. They are all in the gray color. They are in the queue. So, and we need to compare their key values with the current weight, with the weights, right? We need to compare the weights from U to V with the current key of the adjacent vertices. So in this example, the parents attributes of B will be updated to A, and the key will be updated to the weights of the edge from A to B, right? Because the key is originally infinity, and infinity is greater than any number, okay? So it becomes 4, and same for H. Its pi parent is updated to A, and the key is also attributed. So now after A is popped out, the minimal priority queue is updated. Now we have two non-infinity. We have two actual numbers. It's for B and H, and this is their key values. And the B is highlighted because B has the minimal key value. So B will be the next one being popped out. Okay, so in the next iteration of the for loop, B will be popped out. Okay, and after B is popped out, all of B's adjacent vertices will be examined. Okay, and so after B is popped out, because the B's parents is already set to be A in the previous step, okay, in the previous iteration, the parent of B is A, so we'll have this edge highlighted, indicating the tree path, or indicating the tree edge. And A is the root and B is its descendant, is its child. Okay, so after B popped out, we'll need to check the adjacent vertices of B, which is H and C and A, right? A is still its adjacent vertices, but since A is already outside the queue, we don't need to compare the key of A again. We only need to do what we need to do is to update the pi parents of B of C by setting the C.pi to B and updated the key of C. But we don't need to update the parents of H because the key value for H is 8. Remember, the old value for H is 8, but the current edge from B to H is 11. It's bigger than the key, so there's no need to update it, right? That means the distance from the H to the tree is 8, not 11. 11 is longer, so that's not the actual light weight, right? The light weight is from A to H. Okay, so this step, we don't need to update the values for H. So as a result, we will have new values in the queue, which is C and H. H is not changed, but C is changed. Okay, so in the next iteration, we have a tie, right? We have C and H, and we randomly update, we randomly pop out an element from the queue, and assume that we popped out C. But it's also possible we can pop out H, and the resulting procedure will be a little bit different, but it's okay. It's essentially the same. So C got popped out, and we need to check all adjacent vertices from B, I, G, from B, I, F, and D, right? So accordingly, we need to update the attributes for D, F, and I, and B doesn't need to be updated because it's outside the Q. So now the Q looks like this. So the I is highlighted. So the I is closest to the tree, and I will be popped out in the next step. Okay, and the I's attribute adjacent vertices will be checked, which is CGH. Okay, CGH. Now H is updated, right? Remember the old value of H is 8, but this time the weight from I to H is smaller than H, which means, okay, now we need to update your key values because your distance, your shortest distance from H to the tree is now this path rather than this 8 path. Okay, so now we need to update it. Okay, so F will be the next one being popped out. Okay, and the Q is updated, and then G, and then H. Right, now we only have 2 elements left. So D will be the next one being popped out, and E will be the next one being popped out. Okay, and until we reach the empty Q, we will have a complete minimal spanning tree that is constructed now. And the tree, all the relationships between the vertices in the tree are indicated by the parents attributes, the pi attributes. So starting from the root node, we can able to draw the tree structure really quickly. Okay, so that is the Prim's algorithm. So as you can see, what in the process of constructing the minimum spanning tree, we are growing the tree, but we are not merging different parts of the forest, right? The tree is growing incrementally, and all the edges in the tree are actually connected, not separate from each other. All right, so that's the difference, as you can see, from Prim's algorithm to the Kraskow's algorithm. So next, let's analyze the running time for MST Prim a little bit. So it's basically the same analysis we need to make. So the initialization takes big O of V times because we need to go through all the vertices. Okay, and now keep in mind that we have a minimal priority queue maintained and implemented. So the extract mean operation, it'll take big O of logarithm of V. So if the minimal priority queue is implemented by a minimal heap, then because any heap operation takes logarithm running time, so the extract mean will take a big O of logarithm V time. And there's in total V iterations in the while loop because there's only, because all the vertices are in the queue and each vertex is extracted once. So in total, there are V many iterations in the while loop. There are V iterations. Okay, so the total time for calling the extract mean is big O of V times logarithm of V. Okay, because it's the extract mean is executed once for each vertex. Okay, and the body from line 8 to 11, it actually examines all the adjacent vertices for any vertex that is extracted from the queue. So in total, we need to consider big O of E times for all the edges actually, right? If for each vertex you consider all of its adjacent vertices, then actually we're considering all the vertices or all the edges, right? So the body of the for loop executed big O of E times, okay? Then here comes the tricky parts. The line 11, we update the key values, right? The key is part of the minimal priority queue. whenever we update the key value for an element in the queue, all the elements needs to be rearranged because the key is updated. The bigger elements that before the updates may have a higher priority. It needs to be moved into a different position, right? So that's why each updates of the key will implicitly call the minimal priority the minimal heapify operation if the minimal priority queue is implemented by a minimal heap. Okay, so that will also cause logarithm of v time each time we update the key. So in total, we'll have e times logarithm of v associated with these updates, plus the big O, v times logarithm of v here. In total, we can have almost a big O of e times logarithm v. So that is the same running time as the Kraskos algorithm, which means the Prim's algorithm is equivalently efficient in terms of running time than the Kraskos algorithm. But there could be some improvements over the Prim's algorithm, as we will see later. So let's compare these two algorithms a little bit. The Kraskos algorithm and the Prim's one, they use different rules to determine the safe edge, right? The safe edge needs to be the light edge. But in Kraskos algorithm, the light edge is the one with the least weight that connects two distinct connected components or two distinct disjoint sets. So that's the weight is first sorted, right? First sort, and then in the while loop, in the for loop, we'll go through all the edges in the sorted order. So that's the first one who satisfies the condition is always the one with the least weight. But in Prim's algorithm, the safe edge is also the one with the least weights, but this one we maintain the minimal priority queue. And this least weight edge is connecting a tree to a vertex. They are not connecting two trees. It's not the connection between two disjoint sets or two trees in the forest, but it's an vertex between it's the connection between the tree and a vertex that's outside the tree, okay? And lastly, the Prim's algorithm can be faster. If we implement the minimal priority queue with a more advanced technique like a Fibonacci heap, the running time can be further improved from e times log v to v times log v. Okay, so this is something we can know about. Okay, and that's basically it for the minimal spanning tree problem. So I think I'm gonna end the lecture today a little bit earlier because I think the content so far is a little bit dense, and I hope you can spend more time review the slides and or reading the textbook. So I will release the quiz questions on the canvas about the minimum spanning tree problem, and also I will release the assignments 4, release all the questions, problem sets for assignments 4. So for next week, it's Thanksgiving week, and but the Tuesday class will still have one class because the school is not closed yet, and we will have a class on Tuesday so we can get a start for the second type of minimum for the advanced graph algorithm, which is a single source shortest path problem. We'll get it started, and then it will be the break. And after the break, we will continue the rest part of the graph algorithms. And that is basically the plan for this winter break, for this Thanksgiving break. Do you have any questions?